In this video, I'm going to explain how to compare statements in propositional or sentential logic for the purposes of determining whether the two statements are logically equivalent, logically contradictory, logically consistent with one another, or logically inconsistent with one another. As I'll explain as we move forward, but let me restate it initially here. Two statements are going to be logically equivalent if they have the same truth values in every possible world when we do a truth table for both of them. So in a world where one is true, the other is true, and in a world where one is false, the other is false. Two statements are going to be logically contradictory if they have opposite truth values in every possible world. And two or more statements are going to be logically consistent if there is at least one possible world in which they are true. And two or more statements are going to be logically inconsistent if there is no possible world or no line in our truth table in which they are true. So let's get into a simple example to start with. So suppose that I have, or we're going to start with these two statements. It is not the case that either A or B. So that's statement number one. Statement number two is not A and not B. So these statements have the same atomic propositions, and that's what allows us to compare to determine whether they are equivalent, contradictory, consistent, or inconsistent. So I'm going to start by initially populating my starting truth values. And since I have two atomic propositions, I am going to need 4 lines in my truth table. And since I'm going to have 4 lines in my truth table under my first atomic proposition, which is A, I'll do half trues and half falses. And then I want to make sure I duplicate that over here, because there cannot be a world in which A is both true and false. If A is true here, it has to be true here. I divide the number of trues and falses that I alternate by 2. And so in that case, that just means I alternate true, false under my second atomic proposition. And that's my initial assignment of starting truth values. I can now go through and, using the truth functional relationships, assign my truth values for the logical operators. So let's start with this statement. So if A is true and B is true, then the claim A or B is also true. If A is true and B is false, the claim A or B is itself true. Same with this one. But if A is false and B is false, then the claim either A or B is itself false. And now, when I go to the negation, because so far I was just considering the claim either A or B, but this formula says it is not the case that A or B. So now, under the negation, I put the opposite truth value for the claim that it's negating, which is the disjunction. So false, 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 true. Now I'm going to go over to my second proposition. This is a conjunction of 2 negations. So I have to start by doing my negations and then end by doing the column under the conjunction. So trues become falses and falses become trues. And then a conjunction is true only when both conjuncts are true. So in this case, because not A is true and not B is true, but in all other cases, it is false. Now, What I need to do to compare the truth values is look at the main operator in each case. So I'm looking only at the main operator, and I'm checking to see whether is there a line in which they are both true. There is, so they're logically consistent. But beyond being logically consistent, they are logically equivalent because on every line they have the same truth value. So we say, in comparing these, that they are logically equivalent. Let's do a more complicated example now. So I'm going to start with the claim. Let's see if you can see that. Yep. If both A and B, then not C. That's my first proposition. My second proposition, I'm going to just put a solid bar there so we distinguish the two propositions. My second proposition is going to be much more complicated. I'm going to write it out and then I'll read it to you. It's so long that it barely fits on the page. So the second formula is a conditional claim. So the way that I would read it is that if either C or B, or both not B and A, then either C or not B. Okay, so we have 3 atomic propositions in both formulas. And so I'm going to need 8 lines in my truth table. And so I'm going to start by putting 4 trues and 4 falses under my first atomic proposition. Under the second, I'm going to divide the number by which I alternate true and falses by 2. So I'm going to do 2 trues, 2 falses, 2 trues, 2 falses. Then I'm going to further divide by 2 again for my third atomic proposition. That results in me just alternating trues and falses. And in adopting that process, I've thereby ensured that I have exhausted all of the possible combinations of the possible truth values for each atomic proposition. Over on the second formula, I need to make sure I'm using the same arrangement of truth values that I did in the first formula. So C is alternating true and false by just 1. B, I did 2 and 2 as my alternating pattern. B again. A was 4 trues in a row and then 4 falses. C again is alternating by just 1. And B again is 2 by 2. So this is just the initial assignment of all possible combinations of truth values for the atomic propositions. Now I need to do the truth functional assignment of truth values. I'll start here. So it's a conjunctive claim, so it's true only when both conjuncts are true. In all other cases, it's false. Not C, I just swap out the opposite truth value. The conditional claim is false only when the antecedent is true and the consequent is false. In all other cases, it's true. So I'm looking for that true, false arrangement, and then it's false. In all other cases, it's true. Switching over to my second formula, I'll start with my disjunction, which is true as long as one of the disjuncts is true. In all other cases, it's false. Here I have a negation. And now I have a conjunction of my negation and A. So that has to be, I have to have two trues in order for it to be true. In all other cases, it's false. And now I have a disjunction of these two claims. So I look at this line and this line. So true, false means true. True, false means true. True, false and true, still true. True and true, oops, true and false, rather, is still true. True, true. And the only place in which it's false is where I have two, both disjuncts are false. Okay. Over here, again, I have a negation. And I have a disjunction. And now I have a conditional claim. And so I'm looking at, let me highlight it. I'm looking at this line and this line. And again, it's only going to be false where the antecedent is true and the consequent is false. In all other cases, it's true. Okay, now when I'm comparing the two statements, I'm going to need to look at the main operator in each statement. So in that case, it's this column and it's this column. And they are not logically equivalent because I see that I have, like just on that first line, this claim is true, but this claim is false. So they're not going to be logically equivalent. Are they logically contradictory? Well, on line 1, they do contradict each other. On line 2, they do contradict each other. But on line 3, they do not, because they're both true. So what that means, there is a line on which both are true, and since they're not logically equivalent, I would say they are logically consistent. There's a world in which both propositions could be true or would be true. Okay. Let me do now one, demonstrate a logically inconsistent set of formulas. So I'm going to start with, it is both the case that both A and B and not C. That's my first proposition. My second that I'm going to compare it to is both A and B if and only if C. Okay, so since I have 3 atomic propositions, I again need 8 lines on my truth table. We always want to make sure that we're being consistent and duplicating the initial assignment of truth values in each instance of an atomic proposition. Okay, and now I can go through and do my truth functional, the assignment of truth values given the truth functional relationships. So contradictions are always easy. Conjunctions, I'm looking for two trues. In all other cases, it's false. Same here now, but I look at this line and this line, so true and false, false, true and true, true, false and false, false. I'm going to make sure this one's clearly an F. It's going to be false in all other cases. Over here, true, true, false, 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 false. And the biconditional is true whenever the truth values of the propositions it's joining together have the same truth value. So either two trues or two falses. So true and true means true. False and false means true. Okay. Now I can compare these statements. To compare them, I look at the main operator in each statement. And I'll start with the first row. What I see is false and true. So they're not going to be logically equivalent. And so far they're not logically consistent, but I'll keep going. So now here I have false and true. So far on lines 1 and 2, they've contradicted each other. Line 3 is false and false. So they're no longer contradicting each other, but false and true, false, false, false and true, false, false, false and true. So although they do not contradict each other, because there are these lines on which both are false, there is no line on which both are true. And so we say they are logically inconsistent. All right, I'm going to end the video there because we're already at 17 minutes. It's longer than I anticipated. Take a look at the exercises and see if this is sufficient to equip you to do the exercises that I posted yesterday, and bring questions that you have about how to do this to class on Tuesday. Have a good weekend.